So we're going to do in this session only binomial capability analysis as an example, and we'll have two examples. The first step, okay, we confirm that the process is stable. We've done that, and in the control section, again, we'll look at that in more detail in course 2. We're going to assume that our process is stable, so we can check, and then we're going to be calculating the defects per unit, or total number of defects over total number of units that we're measuring. We then want to convert this to, or we can convert this to a ppm, because again, the defect rates tend to be rather small. And if we know the number of opportunities per part, the number of defect opportunities per part, we can calculate our DPMO, which is again the DPU times a million, which is DPM over the defect opportunities for 1 unit. And then we can convert this to a sigma level or sigma capability. So, as an example, let's assume our process is stable and our customer is requiring a sigma capability, a sigma level of greater than 4.0. Last month, we measured 20,856 units were produced over 21 days. And of these, 292 were defective. And here for this example, there's one opportunity for a defect in every part. So did we meet the customer requirements? Well, DPU, total number of defects over total number of units. So we have here 292 divided by 2856. And we get here then 0.01400, which is equivalent to 1.4%. Now, we've said there's only one opportunity for a defect in every part. So if we calculated the ppm, then we would multiply this 0.01400 by a million, and we would get 14000.8, our ppm. The DPMO, again, this total opportunity for a defect in 1 unit is equal to 1. So this actually is equal to the ppm. So we have 14000.8 also for our DPMO. Now, we have then our capability level, our sigma level, the 1.5 sigma shift, as we did. We're going to look at that one more time. Do you remember this? So we had that for the Six Sigma methodology. Motorola provides for the fact that the processes are expected to drift. A Six Sigma capability allows for a drift of 1.5 sigma distance from the center. And this gave us this famous 3.4 defectives, or 3.4 parts per million defective. And what this meant was if we had a CP of equal to 2, so as we showed here, if we had a process that had the specifications that were located, so USL minus LSL equals 12 sigma, then the CP is going to be USL minus LSL over 6 sigma is equal to 2. Remember we did that before. If this drifts off target, I'm not drawing this too well here. Oops, I really didn't draw that too well. Hang on. Radia. Let's try that again. Okay, oops. If this drifts off, so here's the 1.5 sigma shift here. And so now I want to basically draw the same curve. If this drifts off here, this is where you would see, this is basically nothing out of spec, and here you get the 3.4 ppm. So this corresponds then to a yield of 99.99966%, which are in spec. Now we then took that and we converted that to the sigma capability level. So 99.99966 gave us a ppm DPMO in this case because we have one defect, assuming one defect opportunity, and a sigma level of 6. So we've done that before. Now, our example where we had, let me go back a couple slides here. In this example here, where do we find that yield number? Well, we have one opportunity for defect in every part. That means for every part, for every defect, we get a defective. So every defect equals a defective part. So the yield then is going to be 1 minus this 1.4%, 0.014, is going to be equal to 98.6%. If I make that a little clearer, 100% minus 1.4% is 98.6% yield. Okay, so going back then, we have here yield equal to 98.6%, and we can look in our table, 98.6%. Okay, this is not exact, but our table here we can see 98.61, or actually, here between 98.57 and 98.61, so we're looking very close to around, Z is around 2.20, or you could, somewhere between 2.19 and 2.20. So let's take, for simplicity's sake here, 2.20, so it's super exact. And what we can see then is that for Z is about 2.2 or 2.20 plus that 1.5 shift. This gives us then an equivalent sigma capability of 3.7. And what does that mean? Well, we do not meet the requirements of a sigma capability of 4.0. We're below it for this example. So 2.92 defective out of 20,856. If we do our calculations, we come up with a sigma capability of 3.7. So let's look at another example. This time we have a stable process. Again, same customer requirement, sigma capability greater than 4. And the same thing, we have 20,856 units produced. 292 were defective, but this time we have 10 opportunities for defect in every part. How is this going to change things? I think some people can already see how this is going to work. So we calculate our DPU, total number of defects over total number of units. We get the same number, right? Nothing's changed there. Some O's in there if you want. Gives us then also a ppm. It's going to be the same thing. So 14000.8 ppm. But now the DPMO is going to change, right? We have 10 opportunities for a defect. So here we have the 14000.8 divided by 10, right? Which is going to give us 1400.08. So we also, I didn't mention this earlier, but a lot of times you end up with another measure. Maybe I write it down here. The defects per opportunity, which is the DPU divided by the opportunities, defect opportunities in one unit. And this just helps us with calculating yield. So the DPU was 0.01400. So from here, divide this by 10, and you get 0.0014, which is equal to 0.14%. I really hope I don't make a mistake here. Always do. But so instead of 1.4%, now we only have, with this 10 opportunities for defect in every part, 0.14%. So our yield then is equal to 100% minus 0.14% is equal to 99.86%. I'll show that again in a minute. So, and then we would convert to a sigma level. So, yield 99.86%. Let me write that again, 0.86%. That's, of course, is equal to 0.9986. Let's look for this. 0.9986. I can see, actually, we're looking like it's somewhere around here. Again, the tables are not, it's when you do this with with Excel or with your computing program, but here we'd like to still like to use our tables. So we're looking around, Z is around what? 2.99, something like that, 2.98, 2.99. And then, so again, here's all the information. Here's our new DPMO that we just calculated, 0.14%. And here, the yield, we're looking then at a Z of about 2.99 plus 1.5 gives us a sigma level that is now 4.49. And this means we are meeting our customer requirements. So if there's more, this is wrong, there are 10 opportunities for defects in every part. Okay, good. Then I hope that gives you an idea of how, with discrete data, with attribute data, looking at the number of defects and knowing the number of defects per part, we can then perform a discrete attribute capability analysis so that we can come up also with this capability, the sigma capability level for our process.